Remember that this is part 3 of 4 on the section on cardiac muscle contraction. Next, we'll talk about the Frank-Starling relationship. The length-tension relationship for ventricular systole has already been described. This relationship now can be understood using the parameters of stroke volume, ejection fraction, and cardiac output. The German physiologist Otto Frank first described the relationship between the pressure developed during systole in a frog ventricle and the volume present in the ventricle just prior to systole. Building on Frank's observation, the British physiologist Ernest Starling demonstrated in an isolated dog heart that the volume the ventricle ejected in systole was determined by the end-diastolic volume. Remember that the principle underlying this relationship is the length-tension relationship in cardiac muscle fibers. The Frank-Starling law of the heart, or the Frank-Starling relationship, is based on these landmark experiments. It states that the volume of blood ejected by the ventricle depends on the volume present in the ventricle at the end of diastole. The volume present at the end of diastole in turn depends on the volume returned to the heart, or the venous return. Therefore, stroke volume and cardiac output correlate directly with end-diastolic volume, which correlates with venous return. The Frank-Starling relationship governs normal ventricular function and ensures that the volume the heart ejects in systole equals the volume it receives in venous return. Remember that a previous discussion had in the steady state cardiac output equaling venous return. It's the Frank-Starling law that underlies and ensures this equality. That is, as venous return goes up, the heart is able to generate a greater cardiac output to compensate. The Frank-Starling relationship is illustrated in figure 4-22 on page 144. Cardiac output and stroke volume are plotted as a function of ventricular end-diastolic volume, or right atrial pressure. On the bottom, in the x-axis, you can see ventricular end-diastolic volume increasing from left to right. And you can also see this as increased venous return, because as venous return increases, the right atrial pressure will go up. The way to think of this, though, is increased pressure in the heart prior to systole, meaning end-diastolic volume, as it increases, will cause an increased stroke volume, as evidenced by the upward sloping graph. Cardiac output and stroke volume are plotted as a function of ventricular end-diastolic volume, or right atrial pressure. Right atrial pressure may be substituted for end-diastolic volume because both parameters are related to venous return. There is a curvilinear relationship between stroke volume, or cardiac output, and ventricular end-diastolic volume. As venous return increases, the end-diastolic volume increases, and because of the length-tension relationship in the ventricles, the stroke volume will increase accordingly. In the physiologic range, the relationship between stroke volume and end-diastolic volume is nearly linear. That is, as the end-diastolic volume goes up, the cardiac output goes up. Only when end-diastolic volume becomes very high does the curve start to bend and go flat. At these high levels, the ventricle reaches a limit and simply is not able to keep up with the venous return. Also illustrated in figure 4-22 on page 144 are the effects of changing contractility on the Frank-Starling relationship. Agents that increase contractility have a positive inotropic effect, that is, the uppermost curve. Positive inotropic agents, such as digoxin or dopamine or dobutamine, produce increases in stroke volume and cardiac output for a given end-diastolic volume. The result is that a larger fraction of the end-diastolic volume is ejected per beat, and there is an increase in ejection fraction. Figure 4-22 is shown here. On the control bar, which is in purple, you can see that as the ventricular end-diastolic volume increases, the cardiac output increases. You can also see the effects of positive and negative inotropic effects for a given ventricular end-diastolic volume on cardiac output. Agents that decrease contractility have a negative inotropic effect, which is seen in the lowermost curve. Negative inotropic agents produce decreases in stroke volume and cardiac output for a given end-diastolic volume. The result is that a smaller fraction of the end-diastolic volume is ejected per beat, and there's a decrease in ejection fraction. Next, we'll look at the normal ventricular pressure volume loop. The function of the left ventricle can be observed over an entire cardiac cycle, diastole plus systole, by combining the two pressure volume relationships from figure 4-21. By connecting these two pressure volume curves, it is possible to construct a so-called ventricular pressure volume loop, which is seen on figure 4-23 at the bottom of page 145. Remember that the systolic pressure volume relationship in figure 4-21 shows the maximum developed ventricular pressure for a given ventricular volume. To facilitate understanding, a portion of that systolic pressure volume curve is superimposed as a gold dashed line on the ventricular pressure volume loop, and that can be seen at the top. The dashed line shows the maximum possible pressure that can be developed for a given ventricular volume during systole, that is, when the ventricle is contracting. Note that point 3 on the pressure volume loop touches the systolic pressure volume curve, which is the dashed line. Also, it may not be evident that the portion of the loop between points 4 and 1 corresponds to a portion of the diastolic pressure volume curve from figure 4-21, which is not shown here. Here's figure 4-23 on page 145. This is a left ventricular pressure volume loop. One complete LV cycle is shown. The dashed line shows a portion of the systolic pressure volume curve from figure 4-21, and we will talk through the different phases of this cycle. The ventricular PV loop describes one complete cycle of ventricular contraction, ejection, relaxation, and refilling. The first phase is isovolumetric contraction, and that is from point 1 to point 2. We will begin the cycle at point 1, which is the end of diastole. And that makes sense because that is the maximum volume, as you can see. At that point, the left ventricular volume is 140 and the LV is at low pressure. And that marks the end of diastole. Isovolumetric contraction is from point 1 to point 2. The LV has filled with blood completely from the left atrium, and its volume is the EDV, which is 140 milliliters. The corresponding pressure is quite low because the ventricular muscle is relaxed. At this point, the ventricle has activated, it contracts, and the ventricular pressure increases dramatically. Because all the valves are closed, no blood can be ejected from the left ventricle. And because the LV volume is constant, although ventricular pressure becomes quite high at point 2, there is no ejection of blood. Therefore, from point 1 to point 2, we have isovolumetric contraction. At point 2, the LV pressure becomes greater than the aortic pressure. That causes the aortic valve to open. You may be wondering why the pressure at point 2 does not reach the systolic pressure volume curve, which is shown by the dashed gold line. The reason is that it doesn't have to. As long as the pressure in the LV is greater than the pressure in the aorta, you will have opening of the aortic valve, and therefore at that point, the LV volume will start to decrease. During this phase, the LV pressure remains high because the ventricle is still contracting. The ventricular volume decreases dramatically as the blood is ejected into the aorta, and that is why at point 2 you have a decrease in the LV volume from right to left. The volume remaining in the ventricle at point 3 is the end systolic volume, and that is the point at which the ventricle stops contracting. The width of the pressure volume loop from point 2 to point 3 is the stroke volume. And the stroke volume here in this example is 140 minus 70, which is equal to 70. At point 3, the systole ends and the ventricle relaxes. Ventricular pressure decreases below the aortic pressure and the aortic valve closes. Although ventricular pressure decreases rapidly during this phase, the ventricular volume remains constant from point 3 to point 4, and that's why this is called isovolumetric relaxation. At point 4, the ventricular pressure has fallen to a level that is less than the left atrial pressure, which causes the mitral valve to open, which is the left AV valve. The left ventricle then fills with blood from point 4 to point 1, and this is a filling from the left atrium passively and also actively as the left atrium contracts. The left ventricular volume then increases back to the EDV of 140 milliliters. During this last phase, the ventricular muscle is relaxed, and pressure increases only slightly as the compliant ventricle fills with blood. That pressure increases according to the diastolic curve, as we saw previously. Figure 4-24, which is shown on page 146, shows changes in the left ventricular pressure volume loop. At point A, we see the effect of increased preload. In point B, we see the effect of increased afterload. In point C, we see the effect of increased contractility. The normal ventricular cycle is shown by the solid lines, and the effect of the change is shown by the dashed lines. So we will go through these examples. The ventricular pressure volume loop can be used to visualize the effect of changes in preload, changes in afterload, or changes in contractility, and these are shown in figure 4-24 on page 146. The solid lines depict a single normal ventricular cycle and are identical to the PV loop which we saw previously in figure 4-23. The dashed lines demonstrate the effect of various changes on a single ventricular cycle, but they do not include any compensatory responses that may occur later, so these are acute changes to the left ventricle. Figure 424a illustrates the effect of increased preload on the ventricular cycle. Remember, preload is equal to end-diastolic volume. In these examples, preload is increased because venous return is increased as well. This increases the end-diastolic volume, which is 0.1. So 0.1 shifts to the right. In this example, afterload and contractility remain constant. As the ventricle proceeds through its cycle of contraction, ejection, relaxation, and filling, the effect of this increase in preload can be appreciated because the stroke volume, which is measured by the width of the pressure volume loop, increases. This increase in stroke volume is based on the Frank-Starling relationship, which we talked about previously. That states that the greater the end-diastolic volume, the greater the stroke volume ejected in systole. Remember, this has nothing to do with contractility. It has only to do with the length-tension relationship. Figure 4-24b illustrates the effect of increased afterload or increased aortic pressure on the ventricular cycle. In this example, the left ventricle must eject blood against a greater than normal pressure. In order to eject this blood, the ventricular pressure must rise to a greater than normal level during the isovolumetric contraction, which is 0.2, and then also during ventricular ejection from 0.2 to 0.3. A consequence of the increased afterload is that less blood is ejected from the ventricle during systole. Thus, stroke volume decreases. More blood remains in the ventricle at the end of systole, and end systolic volume increases. You can see that as a shift in 0.4 from the left to the right. You can envision the effect of increased afterload as follows. If more of the contraction energy is spent in isovolumetric contraction, as you can see from 0.1 to 0.2, as 0.2 is elevated to match the higher afterload, then less of the contraction is left over and available for ejection of the stroke volume, and that is why 0.4 and 0.3 move to the right. Figure 424c shows the effect of increased contractility on the ventricular cycle. When contractility increases, the ventricle can develop greater tension and pressure during systole and can eject a larger volume of blood than normal. The stroke volume increases, as does the ejection fraction, and less blood remains in the ventricle at the end of systole, and consequently, the end systolic volume decreases, that is 0.3